Hello everyone, myself Raj Chakraborty working at ICS under the supervision of Professor Amlanjyoti Pal. Today I am going to present my work on dynamic response of AC driven LED based on perovskite materials. Now, hybrid halide perovskite are considered for a wide range of application in the domain of optoelectronic devices due to their interesting optical and electronic properties. The dynamic response of AC perovskite LED is moreover interesting due to the ambipolar nature of the perovskite material, since a balance in carrier transport is always essential to achieve a high brightness at a low driving voltage. Now, when we apply DC voltage, EL can be observed in positive voltage section. Under a DC voltage, double injection of charge carriers occurs when the barrier height for the carriers are low. Following the double injection of charge carriers, band-to-band additive recombination occurs to get EL emission. No EL has been appears under a negative voltage, since the barrier height for the injection of both the type of carriers are high. These results are in good agreement to the band diagram of the heterojunction. Now, when we apply a AC voltage, EL can be shown in both direction. EL in negative cycle arises due to the effect of the residual charge carriers in the devices. That is, during a positive half cycle, uh, the charge carriers are injected with ease. Some of the carriers recombine to yield EL emission, while the rest of results in device current. That is, at this stage, when the voltage tends towards the negative cycle, the movement of injected carrier starts to move towards the direction opposite to the previous one. In doing so, they again get an opportunity to recombine and results in EL emission in the negative direction of an AC voltage. Now, we have plotted the EL minus to EL plus ratio, where we can see that the EL output in the MAPB BR3 device under the negative cycle of an AC voltage is much less than that in case of MAPB I3. Being MAPB I3 as a amipolar material, the carrier are available throughout the device for additive recombination. On the other hand, in a relatively unipolar MAPB BR3, injected electrons remain concentrated near the electron injecting layer due to their low mobility. Now, at high frequency, the duration of a forward bias half cycle becomes less than the transmit time of two types of carriers across the active layer. As a result, EL peak does not appear at the crest of a sinusoidal voltage, as longer time is required for the carriers to meet and recombine radiatively. A larger phase lag is in unipolar MAPB BR3 device occur due to the recombination nearer to electron injecting layer of the perovskite. Now, here we have studied the frequency response of AC LED, where we can see that the at low frequency, the EL intensity are frequency independent, and it decreases at higher frequency. The 3 dB frequency, which is the limiting frequency of device operation, increases with increasing I3 iodine content in the material. Now, this figure shows that the thinner device operated till a higher frequency. Similarly, higher voltage pushed a device to function till a higher frequency. And the results are quite obvious, since the time width of a half cycle should be shorter for thinner device, so that the device may recombine till a higher frequency. Likewise, a higher voltage drives the carrier across the device within a short time, implying the requirement of smaller half cycle of a higher frequency in enabling radiative recombination and thereby EL emission. So I conclude with this, and thanks for listening.